All right. Welcome, everyone. My name is Casey Wang, and I'm a co-PI on the Fabric project. Thank you all for joining us today for the 8th installment of our Mastering Fabric Tips and Tricks webinar series. Today, it'll be led by Ganesh, Chennimalai, Sankaran, and Cong Wang. Next slide, please. Before we begin, I'd like to share a few housekeeping items. First of all, the webinar will include a live Q&A question and answer session following the presentation. So the chat feature of your Zoom should have been disabled. If at any point you have a question, please feel free to go ahead and type it into the Q&A box at the bottom of your Zoom screen, and we will answer it during the Q&A session. And this webinar will be recorded, and after it, we'll be sharing that with all the registrants. Next slide, please. We're joined today by one of our presenters, Ganesh Chennimalai Sankaran. Ganesh has his bachelor's in electronics and communications engineering, and then higher degrees in computer science engineering. Ganesh has 2 decades of industry experience working for HCL Cisco, and then for Dell Networking. Ganesh's expertise spans network management, network security, and network operating systems. Ganesh has been a part of 3 startups that have developed a mobile application, SD-WAN, and optical computing hardware, respectively. Ganesh has co-authored 30 research articles and has been the primary contributor to 25 patents, including pioneering contributions to change detection and drop accounting, programming network switches, computing at higher data rates, and designing converged hardware for computing and communications. Next slide, please. Today, we're also joined by Cong Wang. Cong Wang is a senior researcher at RENCI, UNC Chapel Hill. He has his PhD from University of Massachusetts Amherst. Cong Wang has co-authored more than 40 papers with focus on networking, cloud, and distributed systems, and AI, ML, AI, machine learning for infrastructure. Now I will pass it on to Ganesh to begin the presentation.
Hi, everyone. I'm Ganesh, and I'll be walking you through the Tofino switches for network research and beyond webinar today. This is the outline for today's talk. We will be looking at what are Tofino switches, a little bit of an introduction, and then Tofinos in Fabric, how you can use Tofinos in Fabric, how it is available, and so on. And then we will look at P4 programming, which is actually closely tied with Tofino switches, and how you can program the Tofino switches using P4, and a little bit of into the context of using P4 programming on Tofino in Fabric type of thing before we actually look at a demo, and then we wrap up with a couple of suggestions and recommendations that we have. So first of all, what are Tofino switches? They are actually programmable switch ASICs. Tofino 1, which is the version 1, it supports 6.4 terabits per second, which is like 3200 Gbps duplex, full duplex ports can be supported by Tofino 1 switch, and Tofino 2 is actually 2 times this, and so on. So these switches have a, in terms of architecture, they have a multi-pipeline shared buffer. So which means that it is not a single pipeline. So of the 32 ports, for example, 8 ports are actually attached to one processing pipeline, and the next 8 ports are attached to another pipeline, and so on. So that can be like 4 pipelines, and that way it increases the overall processing capability. So each pipeline, roughly, you can imagine it supports like 1.6 terabits or something like that. So put together, all the 4 pipelines will support 6.4 terabits. And then the internal bus bandwidth is actually pretty huge. It has like 4096 is the bus width that we are looking at when we are talking about the internal bus. Uh, so what it means is like usually we have if we have to compare the CPUs, this is like we are talking about 64-bit and 32-bit. So this is actually a huge bus width that we have, and pretty much the entire header can be transported in one clock cycle across the bus from one stage to another, as we'll see later. So there is actually a buffer that is available, which is actually 22 MB. Though it looks very small, this is you need to compare this with the level 1 cache of a CPU. This is typically like realized using static RAM cells, which are actually more power consuming. And that's the reason they don't have very huge buffers. Uh, and this also places another restriction uh, implicitly on the switching pipeline, because you can hold packets only for like 22 MB is like at 100 Gbps or like 64 terabits. It is going to be worth a few microseconds or maybe a little bit more. But that's the overall traffic that you can actually hold. So you need to actually be able to switch the packets within that time. So that places a very strict timeline there. And it also has a 25 gig SerDes, and there are 256 of them, which like together creates a 6.4 terabits pipeline. So if we look at the entire architecture of the switch that is shown on the right hand side, you can see the blue blocks that are actually like not programmable, but there is a yellow that is the orange block that is actually programmable, and that's the only thing that is available for programmability, and we will be focusing more on that. And next, we will look at the pipeline. Internally, I have expanded the processing pipeline, and you can see that there is a parser, there is a match action unit, which takes some packet header or some internal variable as the key, and it's like a lookup table. We will see more details later, and it is followed by a deparser. Deparser is the complementary component of the parser. While the parser actually it extracts the header fields, deparser actually puts together all the header fields, and it makes the packet ready for shipment. So there are two stages like this. One is on the ingress side, and the other one is on the egress side. So there are two similar pipelines that are available. If we want to do any egress processing, then we can do so. We can also choose whether we want to do ingress processing or egress processing here. So we are looking at more closely into the parser part here. The typical TCP/IP stack parser graph is actually shown. So this is what the parser has. Parser has this parser graph, and it is actually trying to move from one state to another. For example, it starts getting into Ethernet, and then whether it has a VLAN header, IPv4 header, IPv6 header, based on the branching condition, it is actually going to go to the appropriate next state, and then it is going to extract the respective header. So that's the parser graph in short. So with Tofino, what we can do is like, say I have a new L3 protocol, exciting L3 protocol that does some very rich functionality that is completely away from, say, IPv4, IPv6. I say have my own L4 for that built. Then I can actually include that into the parser pipeline. without disrupting any of the existing protocol stacks. So the Tofino switches also give a little bit of a capability to parse deep into the payload, which is, you can consider that as extended header or something like that, which is like, for example, DNS header you want to actually parse. You can do parsing of some of the application headers as well. It does not distinguish between L3 header and the L4 header. Like there is no hard limit, as long as the header is actually not like SNMP or something like that, which is actually like largely TLB based, and it can have recursive objects type of thing. It is actually pretty straightforward to parse them out using the with the Tofino switches as well. For example, some people have shown DNS headers, header parsing, and even DNS responders built on Tofino switches. And what else we can do is, it's actually left to experimenters' creativity. In one of the cases, actually, they have taken the a similar hardware, and then they have actually adapted it to like a stock market, where the ticker prices and the stock prices are actually manipulated in the network for latency reasons, and they actually speed up the entire stock market. So with that, we are going to look a little deeper into the Tofino's pipeline architecture a little bit to understand why it is actually giving us better performance when compared to CPU, and where are the limitations. So when we actually look at the CPU pipeline, it is not showing the animation properly, but I think I can actually, the main intention here is the instruction stream that you see on the left-hand side of CPU pipeline and the data stream that is shown on the left-hand side. They both actually are streams, and they actually move across the CPU pipeline with the instruction matching the data and producing the results. So in case we want to actually realize a loop, or there is actually a control flow that is different, what happens is the same instruction stream is actually replayed for a loop, or if there is a different place from where we will have to execute instructions, then those instructions are actually fetched, and then those instructions are streamed into the CPU pipeline, so that CPU can execute those instructions along with the data that is there. So this is the case with the CPU pipeline. If we look at the Tofino pipeline, you can see the marked difference that the instructions are fixed in case of Tofino pipeline. So the instructions are fixed. What that means is like they are pre-programmed, and for example, I'm going to do addition, and in the first stage of the pipeline, that that is actually applied on to pretty much every packet unless it is conditional. Say, for example, I want to do only for this particular flow, I want to do this addition. Then I can actually, I need to actually use lookup table or something like that to enforce that. Otherwise, it is kind of like a global instruction that is going to be applied uniformly on all packets. So there is no instruction flow change or loops or something like that that is available. You can see that, so it is completely immutable fixed instruction pipeline, and whereas the packets are actually mutable. So when you look at the corresponding data stream, the CPU pipeline data stream is actually a very unit level data stream, which carries, like, for example, one or two operands, 64-bit operands or something like that. But here, the entire packet is actually an operand, and that is actually carried across the stages. So within each stage, it has a rich amount of resources, ALU resources, let it be, or lookup resources, or it can do a lot of vector processing, It can do vector processing up to like 200 bytes in one shot. So you can take 200 bytes of data or header, and then you want to do some kind of like, say, some bitwise operation, crazy bitwise operation, you can do so. But whereas if you compare that with CPUs, it is actually like with the AVX 512, it is supporting something like 512 bits. And here we are talking about 256 bytes. So that's the difference. So it is almost like you can take 1,000 bits at a time and then you can process it. So there is a lot of speculative execution that is available with CPUs, but that is actually not possible in Tofino pipeline. So in one of the papers, we argued that this actually gives a better security if we have to implement some application level logic on the Tofino pipeline, if you understand from that perspective. So we are slightly switching gears and starting to look at Tofinos within Fabric. So Fabric is I should say, US-wide and international research infrastructure that is available for researchers to conduct their experiments. It is specifically meant for researchers, unlike say AWS or other cloud resources that are available, and you can do fundamental experiments on Fabric. So this is actually this diagram kind of captures different sites that are available within the US, and the yellow part represents the terabit core, and the blue ones are the actually gigabit links that are available. And you can see some links that are going out. They are actually going to Asia on one side and Europe on the other side. And there are also links to South America. I think that's not shown here. So this is actually a global network in a way. And we have multiple sites that have this programmable switches. And if you're planning to conduct experiments across sites or at a larger scale, then Fabric is your experimental testbed. So how do you see is like when you go to this, click on one of the sites, it shows up the particular site related resources. And when you click on the particular site, then it shows up the different set of resources that are available. Specifically, if you look at, there is actually uh, P4-SW, if you can see that, star-P4-SW. That's the naming convention that we use for the Tofino switch that is available. And in this particular case, when you click on that, it shows the like whether it is available or not. So we will see later how to see, like if you want to get a Tofino switch, then how you can actually get that and run your experiments on top of it. So this is like on Fabric, we have multiple Tofino switches, as I mentioned, across multiple sites. And out of the 32 ports that we were actually discussing previously, 8 ports are connected right now on Fabric, and each of these 8 ports supporting 100 Gbps. So totally with full duplex, it is actually 8 into 100 into 2, which is like you can conduct experiments that are actually up to 1.6 terabits total. So recently, there was actually a OFC demo where actually they were showing 800 Gbps over the terabit core. So if you are interested in conducting single site experiments with a lot of programmability, or if you are trying to conduct multi-site experiments at this scale, like 500 Gbps or like 1 terabits, or you want to conduct heterogeneous experiments with CPU, GPU, NVMe, and programmable switches in your experiment, or if you want to do something like a distributed data plane where multiple Tofino switches kind of like work together to realize a higher level function. So these are some of the hints or some of the experiments that can be conducted, but this is not the total exhaustive list, and it's up to your creativity to build a new one. So, uh, so recently, Tofino actually comes from Barefoot, and that was bought out by Intel. So they recently outsourced the entire compiler. So we are actually free to use the entire tool chain and create, or like even since it is open source, we can also kind of contribute to the compiler tool chain and experiments there. So we are again switching gears here. Uh, we will look at a little bit of P4 programming. We are still in the introduction kind of stages. Like we introduced Tofino, we introduced Tofinos in Fabric, and now we are coming to this P4 programming in general. So more or less, like we don't need to be pretty much scared to look at P4 as a new programming language. The structure is similar. There are some restrictions that we need to understand. We already looked at the architecture. We are going to look at some of the other things in the next few slides. So if you look at a kind of like head-to-head comparison of how you define structure in C, it is very similar. In a very similar way, you kind of like declare a header in P4. So except for the keyword, I don't think there is a very big syntactical difference. There is, of course, a semicolon that is or a colon that is actually missing in the P4 thing. But if you put a colon, I don't think it is going to complain. So having said that, the bit representations are actually something that are actually pretty close to headers. Most of the headers, like if you already know IP headers, Ethernet headers, they deal with a lot of bits. So 3-bit of this belongs to this field type of thing. In structures, they are actually rounded off typically, but P4 and the programs that are dealing with the packets are very specifically tied to this. They need to extract that 1 bit, and then the 3 bits if those fields actually correspond to 2 separate things. So that is actually taken care. So it is actually a convenience representation, I would say, in this particular case. And if we look at another example, there is no difference at all. If you are writing a if condition here, you can also write a if condition in P4. But the only restriction is where do you place the if condition? You cannot place a if condition wherever required. Unlike C, you can only place the if condition within uh, the match action unit or the stage, as we call it. So within a control function or a control block, you can actually have if condition, but there are actually like a lookup actions that are there. So if you look up for IP address and then you find some action that needs to be executed based on the match, then that is actually within the action, you cannot actually have control flow changes at a high level. So this is actually another example. If you cannot actually, we saw this already. You cannot realize a loop, but what if you had to? Then you need to kind of unfold that. And Tofino 1 supports like 12 stages, and Tofino 2 supports like 24 stages pipeline. So you cannot have maybe like a very large loop or something like that, like 1,000 iterations or something like that. But definitely 4 or 5 iterations are definitely possible. You need to just unfold. And then the next one is actually we are going to look at slightly complicated ones where we don't have a simple equivalent in C. Here we have a state machine that is defined which starts with this is the parser graph or the parser code that we are looking at. So every parser starts with state start that is actually fixed. So start is also a fixed function with which it starts, like the main function in C, which is the entry point. And then it actually goes to like it's self-explanatory, like it extracts some metadata and then it transitions to the next state, which is parse Ethernet, where it extracts the Ethernet header, and then based on whether it is IPv4, IPv6, VLAN, it goes on to extract the next header. This transition select is actually slightly similar to the switch statement that we see in C. The only difference is it can be as complicated as like it can take multiple variables as its argument, and then we can also operate on multiple variables. For example, like apart from Ethernet type IPv4, we can also say that, okay, if it comes out of this particular ingress port, for example, if it comes out of CPU port, you may not want to do this. Or if it is coming out of some XYZ port where there is a different protocol that you want to implement, you are free to do that. And then one of the unique features of P4, again, like apart from parser, is the lookup tables. So this is actually embedded in every stage. You have lookup tables. Like, for example, if you want to do a destination-based forwarding, then you take the IP address, destination IP address, and do a longest prefix match. And then you say that, okay, this goes out of this particular port. So that's the typical thing that happens on the internet. But what if you want to do something else? Then there is actually a wide variety of support for custom lookup tables and custom kind of lookup tables. The exact means here that it is actually an exact match that is performed. You can do a L4 based exact match here, or you can support if you want to do something like something crazy like do a longest prefix match on destination port. Nobody is going to complain because it is what you want, the functionality that you want. On destination port, you can do a longest prefix match, exact match, or a ternary match. Ternary match is like some bits can be actually ones or zeros, and some bits can be actually have to be exactly matching. So that's the ternary match. So it is more or less like how you say is 1 star or something like that. So if the prefix is fixed and the suffix is actually wildcard, then it is more or less like the longest prefix match. But if you want to actually kind of like mix and match them, 1 star, 2 star, 3 star, something like that, then that is actually quite possible. So it provides a rich set of lookup functions, and with each pipeline stage, you have lookup tables, dedicated lookup tables to actually achieve this. So that is showing up a little bit of like what kind of P4 works that we have done. We have done optimized routing with smaller routing tables at egress. Typically, routing table routing happens in the ingress. What if we actually switch that to egress? That was actually one experiment that we conducted, and we found that the routing table size can be actually reduced. What this means is currently the routing table sizes are going near millions, and we don't have sufficient hardware resources, and we need to keep upgrading. But if we move to egress, we can actually survive for another few years. So that's the value proposition that it brings to the table. And then we used parsers for regular expression matching because it actually kind of looks similar. If you recall the parser graph, it looks very similar to a deterministic finite automata, and we used that to actually realize some regular expression matching there. And then these are actually like the entire pipeline does not support any floating point operation or advanced math functions. And we started off with implementing floating point operations and log normalization operations, basically logarithm using the lookup tables. So we kind of like pre-program the logarithm functions into the lookup tables, and we use that. And another contribution that we had was actually opening up the processing on switches. to the scientific computing community. Not everybody is well versed with P4. So what we thought is like we can give some convenient methods so that others who are interested in this kind of processing can actually leverage that without it worrying too much about the hardware nuances and things like that. So we also have a deep payload processing for processing high dimensional scientific data, example, a video stream type of a thing. And we will look at the demo at the end of this session. And here is a quick note on some of the P4 targets and when to use them. So there is actually a P4 target that is called the BMB2. This is actually a software based switch. That is pretty much like they had behavioral model V2, and this typically supports like a 1 Gbps data rate or something like that. So it is not meant for mostly for performance evaluation type of things, but definitely we can use this for functionality verification, and it supports deep payload processing. For example, I want to look at 500 byte in my packet. Then not every hardware actually supports that kind of processing, deep payload processing, and you are free to do that with BMB2. There is another model that is available. This is also software-based P4 Tofino model. This is more similar to the Tofino switch hardware. So this is more like a simulator type of thing for Tofino. You can use this for actually verifying like the compilation issues. You can iron out all the compilation issues. There are a few hardware restrictions. The compiler is not as sophisticated as like a GCC type of thing. So a lot of data dependencies and a lot of program dependencies have to be handled manually, and we have to actually break it down so that the switch understands what needs to be done. So it is more like that. It's not like you write a higher level function and you are done with it. It is not to that level yet. So there is also another target that is available, which is DPDK based, where the software switch apparently uses some of the DPDK based support, DPDK support, and it can support more than 10 Gbps. And last I heard, there was a team that was actually trying to do something like 100 Gbps experiment with P4 DPDK. So it can go until that, and with the DPDK support. So it is more or less like you can pretty much leverage the flexibility of BMB2, but at the same time, you can also use P4 with the DPDK to actually scale it up, kind of thing. And then there is actually a P4 FPGA target, so which leverages the FPGA. There are multiple workflows and multiple notebooks that are available in Fabric. I wouldn't get into this at this point in time because it's actually an elaborate topic in itself. But feel free to actually look at the respective Fabric notebooks related to FPGA, and you will find some of this very interesting. If you want to do something like more than 100 Gbps processing, or like 400 Gbps, 500 Gbps type of processing, then you are free to look at this. And FPGA also supports a little bit of deep payload processing. So whereby you can actually look at some random byte in the payload, deep into the payload, and you can do some processing based on that. It just not you need not be confined with the headers. For example, a stock price is like more than 1,000. I can actually forward it to somebody else, and a stock price is less than some value, then I can forward it to somebody else. Like most of this is used in industrial control systems, and also in IoT based kind of scenarios where you have to do a lot of network based correlation, for example. And then there is our P4 Tofino that we have been discussing so far, and It can support in Fabric. It can support up to 800 Gbps, but the switch itself supports up to 6.4 terabits. So the restriction there is it has a lot of other restrictions that we looked at previously, which is like the control flow restrictions. But with respect to the header processing, it can process only up to 256 bytes. There are other switches which I think like one of NVIDIA switches supports up to 500 bytes or 512 bytes to be precise. But I haven't seen a switch that goes beyond that. Recently, NVIDIA is actually having a DPU. We are going to have some of this installed in Fabric, and users are welcome to take advantage of that. But it is actually not here today, but it will be there soon. And one of the real advantages of NVIDIA DPUs is like it's like a smart NIC that is a computer in front of a computer, as they call it. So you can do pretty much any type of processing within the DPU at like 400 Gbps or more. And it has support for hardware regular expressions. For example, you can populate like 5,000 IDS IPS rules into its hardware engine, and you can get the match done, regular expression matching done parallelly on all this 500 rules. So those are some of the things that are available, like deduplication. It supports with a specific hardware engine accelerator, and there is actually encryption decryption support that is available, and it also supports quite a bit of deep payload processing. So when we actually do some experiments in Fabric with Tofino, there are a couple of common pitfalls. I'm actually trying to cover them. So initially, it can give you something like a driver load error. If the driver is already loaded, then it displays this error. Please check this. Sometimes the driver may not be loaded, and it may give you an error. So you may want to keep a watch on this. If the driver is already loaded, then you can ignore this error. And then the next common thing that we see is like the switch daemon is running switch daemon error. When you run the Barefoot or Tofino switch daemon, if there is another instance that is running, the message that you get is not very user friendly. It will say like it will give you like I cannot connect or something like that. It will give you a connection error, but internally it is the switch daemon. There is another instance of switch daemon that is already running, and you may want to actually kill all of them, or like reuse the already running switch daemon. So there are a couple of runtime errors that we can easily see, and for some of them, it is like say the packet is not getting forwarded properly, packet is not getting manipulated properly. I'm trying to do some processing, but it's not happening. So there is actually a in-slice debugging that is actually coming soon. One of our this is a community contribution by Professor Nick Sultana's student, and they have actually built in-slice debugging where you can monitor the packet that is coming out, how many packets are coming out, and whether something that I'm looking for is actually in there. Because it's actually a pain debugging. If you have worked with network switches, it's not like you write a hello world program and you get a standard output telling you that hello world is actually printed. So it's not that interactive. So everything is packet manipulation, and it is pretty difficult to actually kind of like make out if there is a runtime error. And that's not restricted to runtime errors. As you can see, like even some of the compilation errors are actually kind of like you are very cryptic. You need to decrypt them, but it's not my piece of cake. And usually I use P4 Buddy extension, and that uses in turn ChatGPT and OpenAI extension, and it is actually trying to give me a better one. So it is actually, if you are starting with Tofino and you are facing a lot of compilation errors, then I would recommend that you kind of use that so that you can gain grip quite quickly. But after a point, I think when once you are an expert, then I don't think that would match your expertise, unless it is like you kind of give it an input and you kind of build up its intelligence. So initially, I would suggest using that kind of an environment. And now we will be looking at our demo after this, and this is actually a NSF CC Star funded project, and the primary objective that we are looking at in the initial phase is to detect changes in packet payload and classify based on the change detection, which is like if there is a change, then we actually pass it on to the interested parties. But if there is no change, then we can actually drop that payload or the packet itself. So this is a particular use case which involves advanced light source experiment, and it's a scientific computing use case. So here is a quick overview of that. So there is actually a light source which continuously monitors the sample, uh, and it keeps generating packets as it actually monitors. It converts the data, the image frame into packets, and it sends through the network. Currently, what is happening is everything goes to the right-hand side to the store directly, and then it gets stored, and then it gets picked up for processing later on. But the use case that we are looking at is actually closely tied to maneuvering the data acquisition part or the camera in loose terms. So we can actually zoom into a particular place or spatially zoom and then look at a portion of the sample which is of interest to the researchers than actually kind of generating data that is actually largely redundant type of thing. So we are interested in getting the information that is required for the researchers. So that is why we are actually trying to do this in real time and within the network. So in this specific experiment, around 50% of the packets carry redundant data. We want to actually kind of get rid of them, and we also want to kind of provide a feedback, a real-time feedback, so that the camera can be adjusted. It can zoom in, zoom out based on the feedback. So with that, I'm actually going to hand over to Cong for the demo part, and I'll stop sharing now. We will take the Q&A after Cong finishes.
All right. Thanks, Ganesh. So let me share my screen here. Okay, so we are gonna quickly demonstrate a P4 experiment. So that for this experiment, we'll utilize two sites on Fabric. For this example, I'm using Meech and the FIU. So we have the P4 switches on P4 switch sitting at FIU, and node 1 will be the sender node, and node 2 will be the receiver node. So node 1 will send some traffic through our P4 switch and to node 2. And in the meantime, the P4 switch will detect any bit manipulation or integrity errors during the transfer. Here is my Jupyter notebook. So it's based on existing P4 experiment notebook that Fabric already has. So if you have the Fabric Jupyter notebook, you can go to Fabric examples and go to Fablib API, and then find the Fabric P4 Tofino L2 network. And here is the existing example from Fabric. Our experiment we are showing today is slightly different from the example, but the fundamental part will be pretty much the same as the existing example from Fabric. So what we have is that we have a P4 program that we throw into the compiler, and then compiler will load the P4 program into the P4 switch, so that when the switch is handling the packets, it knows what to do based on our customized P4 program. So let me, for time limitation, I'm gonna skip the intro part, because most of the parts should have been covered by Ganesh. So for this experiment, we are gonna first compile our P4 program. We use the BF-P4 compiler to compile the program, and then we load the data plane program into our P4 switch daemon. And also we are gonna configure the control plane, like using the BFRT Python API to populate the action tables. And then fourth step is to use a quick ping to test the connectivity between the two nodes to verify that our P4 program has been correctly configured. And the fifth step is to run our experiment. First, I'm gonna import our Fablib library to get our configurations, and then we configure the experiment slice. I already have a slice up, so I'm not gonna really create a new slice for today, but I'm gonna load the variables into my Jupyter notebook. So later in the experiments, the program can know like some of the important variables. For example, we are choosing the Mich for VMs and use FIU for the P4 switch. And then the slice name would be P4 lab slice and site 1 and site 2. And I'm gonna skip the create slice part because the slice has already been created. So I will show my my slice information. So as we see that the slice is called this, and we have two nodes, node 1, node 2, and we have a P4 switch. And next, we are gonna upload the P4 code to the nodes. So for me, I have my notebook, and I have the folder called P4 Labs. And the lab 1 is the existing example provided by Fabric, and the checksum 1 is my code. So I will upload my my code to my P4 switch, as well as the node 1 and node 2. So basically, I'm just uploading the directory to the nodes. And next, I will compile the P4 program. So what we are gonna do is to first load the SDE environment, and then we run the P4 build.sh script. And after everything's done, we exit. So if everything's working fine, we should see no errors populating from the shell. I think it's working okay. Yep. So, and then we can verify the compilation files. Usually we should see the so-called Tofino folder in the TN checksum, which is our program folder. And then inside the Tofino one, we should see the folder pipe, and we see the output files if everything's working fine with the compiler. So, and then we are gonna start the daemon and configure the switch ports. So the first one is to, we still go into the SD environment, and then we run some installation scripts, and we run the switch daemon to start the P4 switch. And this will usually take about a minute or two to finish. Okay. Now, as we see that for switch D, the driver has been initiated, and then if the server has started, and then we will run some BF shell. We'll run some UCLI commands to verify it's working. We'll use this so-called PM, which is the port manager, and we'll add in the ports that we need, and then we'll use PM show to actually show us what the ports should look like. So we are adding the ports. So port 1 and port 2. And then we enable the port 1 and port 2. And if it's working fine, when we do PM show, we should see this kind of table. So it will show us the two ports, the port 1 and port 2, and both ports are having the speed of 100 gigabits per second. And we see the ports are ready, and the administration ports has been enabled. Also, we should see some number for the frames that has been received. As we see, like if we run PM show 3 times, we can see that the received packets are increasing. So which means the traffic is flowing. And after this, we just put it to sleep. And then the next step is to populate the switch forwarding table into the P4 switch. So what we do is to run this so-called setup.py script, and we replace the ingress and egress ports with the ports that we have set up. So the script is like this. If you look into the Fabric example, you should see a similar setup.py script. So I will not dig too much into the code itself, but what we are doing is to populate the switch forwarding table. And then we'll run some more scripts to actually run the checksum, the setup.py Python script for our checksum program. Okay. So to verify if our P4 program has been correctly loaded to the switch and no errors for the P4 switch, we can run a simple ping experiment. Basically, we initiate 5 pings from node 1 to node 2 and another 5 pings from node 2 to node 1. If it's working fine, then we can execute our SCAPI script. So basically, we use SCAPI to send some syntactic traffic from node 1 to node 2. First, we install the necessary software into node 1 and node 2. I have already installed the software on the nodes, so I think we don't need to do much about this. And then this is block to kind of tail the log files so that we can see the real-time output from the from this both of the sender and the receiver. And lastly, we'll start the receiver on the node 2. So the receiver is this receiver.py script. This is the simple script that we've written. So basically, we initiate a SCAPI receiver script to listen to the traffic, and then the receiver will detect the changes to see if any packets has been manipulated or having integrity errors, like comparing to the checksum. So if like we will see a confusion matrix populated, so we expect to see the true positives and the true negatives. So that means the program is able to successfully identify the changes versus no changes. But we should not see anything for the false negative and false positive if the program is working fine. And for the sender, it basically just sends some synthetic traffic to the receiver, and we are just looking through a few synthetic generated packets. Some of the packets are manipulated, some of the packets are not. So we can see some results from the receiver side. So I will start the receiver and start the sender. Both will be running as a thread. And then we can tail the logs to see the real-time experiment results. As we see that the sender is sending the traffic to the receiver, the numbers should match for the rate. So the sender is sending about 200. I think this should be gigabits per second, and the receiver is receiving similar amount of traffic, and we see that the true positive and true negatives are populating, and while the false negative and false positives are 0, which means our program is able to correctly identify the manipulated data while the traffic is being sent. So yeah, this is what I have, and we are happy to take any questions. So finally, I'm gonna stop this. And
right.
Thank you.
Thank you, Cong. So now with that, we will move into the Q&A session. We will begin with the questions submitted by audience during the presentation. And we have already stopped the screen sharing, so we'll now move on to the questions. The first question that has been asked, so based on what you presented earlier, is that correct that we can hold 22 megabyte of packets at line rate 100 gig?
The 22 megabytes is actually independent of the line rate. So it is the buffer size that is there available within the Tofino switch. So whether we are going to use 100 gigabits or like 400 gigabits, then that's the maximum that it can hold. So higher the rate, lower the total amount of time it is actually in the buffer.
Thank you. The next question, is there a fabric tutorial online for the Tofino switch experiment?
Yes, there is actually a basic P4 example. I think we can take that link and share that. Yeah. I'll do that while we are actually.
Sure, that's wonderful. The next question, are there any examples to get started? I guess a similar question to the previous one, to start with the fabric Tofino switches.
Yeah.
Yeah. All right. The next question, are fabric Tofino switches ready for conducting performance evaluations?
Yes, the entire switch is actually dedicated. So we can conduct performance evaluation at say 100 Gbps or like even at higher speeds. The primary limitation is the network part. Currently we are actually having the total capacity is actually limited by the network. So we have only 8 ports of the of every Tofino switch that is used. But we can actually go beyond that as well. So having said that, network has kind of like a soft isolation, and we are looking at some kind of like bandwidth limiting, and we are looking at providing QoS and dedicated rate on the network as well, which is coming up soon. And with that feature, we will be able to conduct reliable experiments at kind of like at scale.
Thank you. The next question, can I reserve Tofino switches on Fabric in advance? And if so, how do I do that?
There is actually a reservation feature. So interesting question. There is an advanced reservation feature that is coming up, and we should be able to reserve the switches in advance. And currently, it is more or less like at this instant, whatever Tofino switches are available, you can grab that and then conduct your experiments. But moving forward, we are trying to have an advanced reservation system.
Okay, thank you. And I see that, let's see, the next question, how do you figure out the sites that have available P4 switches?
Actually, if you go through the basic example that is there available, I just shared the link. So there is a cell that says like there is a specific API that is available in FabLib that actually gives you kind of like on which sites Tofino switches are currently available. And we can actually use that. That's a very helpful API to identify what resources are available. In general, but it is not restricted to P4 switches only. If you want to reserve some GPUs, if you want to reserve some FPGAs, you are free to do so.
Thank you. Now we're coming to our last question. Both BMV2 and Tofino experiments are supported on Fabric. What's the difference in terms of setting up the two types of experiments on Fabric?
In general, actually, like the BMV2 switch is actually a soft switch, while Tofino is a hardware switch. So BMV2 is more like a virtual machine that is actually created and available for users. Maybe I'll let Cong take over and add his inputs.
Yeah, sure. So BME2 is a software switch, as Ganesh has mentioned, while our Tofino switches are hardware switches. So BME2 switch will provide more flexibility for like prototyping and learning, while like Tofino switches are better for real hardware experiments if you want to conduct more of the production like environment or like benchmarking for P4 switches. Yeah, and also I think P416 and P414 are both supported by BMV2, but only P416 is supported by Tofino switches. So that's kind of different.
Thank you, Cong. Ganesh and Cong also provided some links for the fabric tutorials that were just mentioned. We'll make sure in the slide deck we'll update with those new information as well. Thank you again for our presenters today, Ganesh, Chennimalai, Sankaran, and Cong Wang. In addition to our presenters, we also like to acknowledge some behind-the-scenes team members who have worked together diligently to make this webinar to production. As you can see in the slides, myself working closely with Chelsea Davis, Lena Karalambos, Jayshree Jagannatha. Thank you to the audience for your participation in today's webinar. In addition to the recording of the webinar, we will email everyone who has registered with a list of resources. The slide deck will be shared, and also you'll find a link for the Connect With Us form. We hope that you will reach out to the Fabric team, sign up for Fabric, and ask us any questions for support. Next slide, please. Our webinar next month will be on July 15 at 11 a.m. Eastern Time. This is the Stitching Together Innovation with Fabric Users series. The webinar will be focused on new users, so we would appreciate it if you could forward this information to any relevant users that you know in your communities. As a final reminder, if you're a Fabric users, please submit your Fabric matrix to describe your research, your use of Fabric, and make sure your project description in your Fabric portal is up to date, because these information are actually being read by many people, including the NSF. So we'll make sure we use that information to promote your work, and we will use that for outreach and including some of those information in the website. Thank you again very much, and have a wonderful day, everyone.